Hello everyone, myself Sabina Devi, Assistant Professor, Department of Physics. Now I am going to explain about interplanar distance. So in previous class I explained about Miller indices, right? Okay. So in this class I am going to explain about the interplanar distance. So interplanar distance is nothing but the distance between the two successive planes. Okay. So let us consider a lattice. So inside lattice it has many lattice points and many lattice lines. Okay. So many lattice planes, right? Okay. So the distance between the two successive planes are called interplanar spacing, right? So in this class I am going to explain about how to find interplanar distance. So what's the formula and how to find interplanar distance, right? So let's recall. So in previous class I explained about the Miller indices, right? So Miller indices are nothing but it's a set of three numbers H, K, L. So that was used to designate the planes in a crystal lattice. Okay. So let us consider a crystal lattice. So inside the crystal lattice it has a plane. So we have to designate these planes by using three numbers H, K, L. So that H, K, L is called Miller indices, right? So these Miller indices are reciprocal to the intercepts, right? Okay, so in previous class by using Miller indices, so how to draw a plane and with the plane how to find Miller indices with are discussed in previous class. Okay. So today's topic is today we are going to discuss about introduction to interplanar distance, right? Okay. So introduction to interplanar distance. So how to determine interplanar distance? So what's the use of this interplanar distance in device application? Okay. So these are only today's topic discussion. Okay. So now our empathy part is, so what's the use of determining the interplanar distance? So what's the use? So why we are going to determine the interplanar distance? Okay. So right. So determining interplanar spacing is important because it reveals how atoms are arranged inside the crystal. So its main uses are actually, so it is used to identify the material. So each material has unique d-spacings. By measuring them using the X-ray diffraction, so we can confirm the crystal structure and the phase of the substance, right? So it is used to check the crystal quality. So variations in spacing, so strain, defect or impurities in the crystals. So calculate lattice parameters. So d-spacing helps find the size and geometry of the unit cell. Okay. So this is used to find the lattice parameters. So understanding the physical properties like electrical, optical and mechanical properties depending on the atomic spacing, right? Okay. So support nanomaterial studies. In nanoparticles, changes in d-spacing indicate the size effects and structural changes. Okay. So in simple words, we can say that d-spacing tells how tightly atoms are packed and helps to identify and understand the materials at the atomic level. So interplanar spacing or d-spacing. So let us consider a plane ABC. So it has three dimensions X, Y and Z. So the intercepts are OA, OB and OC. Okay. So intercept value OA is equivalent to A by H. So OB is equivalent to A by K and OC is equivalent to A by L. These are all the intercept values. So intercept are reciprocal to the Miller indices, right? So A is the side of the cube. Okay, let us consider a cube. So cube has all sides are equal. So all has value A. So separate here. A is the lattice constant. OA is equivalent to A by H. OB is equivalent to A by K and OC is equivalent to A by L. Okay. So now we have applied the cosine law. So cos squared A plus cos squared B plus cos squared C is equivalent to 1. So we know we already found the values of A, B, C. So substitute here. So we get d-spacing value d1 is equivalent to A by square root of h square plus k square plus l square. So similarly for the plane ABC, so d2 is equal to A by h square plus k square plus l square, right? So the interplanar spacing D is equivalent to D2 minus D1. So here D2 is 2A by square root of h square plus k square plus l square minus D1 value is A by square root of h square plus k square plus l square. Finally, we get the value A by square root of h square plus k square plus l square. So this is the interplanar spacing value. So this is the formula to find the interplanar spacing value. So A is nothing but the lattice constant. HKL is nothing but the Miller indices value. So if we know the value of HKL and A, we can easily find the value of interplanar spacing. So the applications of interplanar distance are semiconductor industries and material science and X-ray diffractions. So these are all the tools are used to find the interplanar distances. In semiconductor industry, it is essential for epitaxial growth of the thin films. So silicon wafers are often cut along the 100 plane for a device fabrication. So then material science, they are vital for understanding the crystal growth and the impacts of material properties greatly. So X-ray diffraction, the Miller indices also help to predict the diffraction pattern. So this is the crucial for material identification. So these are all the tool applications are used for determining interplanar distances. So X-ray diffraction and electron diffraction, neutron diffraction method, high resolution TIM and atomic force microscopy and X-ray photoelectron spectroscopy. These are all the application tools are used to find the interplanar spacing. So our curiosity challenge is to determine the interplanar distance. So here our problem is, given problem is the crystal, cubic crystal with the A is equal to 4.12 Armstrong. So now find interplanar distance for 100, 110 and 1113. Okay, we know the formula, right? D is equal to A by square root of H square plus K square plus L square. So here the given values are A was given 4.12 Armstrong and the HKL values are 100, 110 and 111. So substitute here, you will get the answer, right? So these are only assessment quiz for you. So let's check and find the answer. Thank you all.